In this problem, we're asked to find the inverse Laplace transform of a rational function again, but a fairly complicated denominator. If you look at the denominator itself, the closest match in the table is the transform of t to the n, which gives us n over s to the n plus 1, and careful, there's also a factorial in that numerator. So if we're looking at something like s to the 4, then what we'd be thinking of is a transform of t cubed. Now we notice we don't have an s to the power 4, we have an s plus 4 to the power 4. So if we think of the forward operation, we would achieve that kind of shift by having an exponential times the t cubed. If we did that, this would be the case where we have e to the at with a equals -4, and when we do that, we replace all s's with s plus 4s, or s minus minus 4s. So what we'd have here is s plus 4 to the power of 4. So that gives us a good idea of what to do, and it would work perfectly if we just had the 2 over the s plus 4 to the power of 4. But we have this other s on top. So how do we deal with this scenario? The way that's guaranteed to work is to turn this into a partial fraction decomposition. If we know what a partial fraction decomposition would look like here, what do we have? We have in the denominator, we have a repeated linear root. We have s plus 4 4 times. And the form for the partial fraction decomposition is to have all the powers of s plus 4 up to the 4th power. So we have cubes, and we have s plus 4 to the 4. And because they're all linear factors, we'd simply have an a and a b and a c and a d, single constants on top. If we were to perform that partial fraction decomposition, we could then find the inverse of each individual term using the same kind of logic we have here. Then take the inverse Laplace of each term. Now it's a perfectly thorough approach. The only downside is, in this case, it would be tedious. We have 4 different terms. If we make a common denominator, we'll have s plus 4 to the power cubed. We'll have to expand that all out. Bleh comes to mind. It's workable, and some of the numbers turn out to be not too bad, but there's a nicer shortcut that we can take advantage of along the same lines of completing the square. Because the numerator is so simple and the denominator is the same term over and over again, what we can do is try to build one of the terms that we see in the partial fractions. In particular, if this was an s plus 4, we could cancel things. So if our goal is to cancel the s in the numerator, we can't just cancel it because there are no s's in the bottom, but there are s plus 4s. So if we simply add 2 and group the resulting terms together, we'll be able to cancel one of the s plus 4s. Now, we can't just go wildly adding 2, but we can certainly add and subtract 2 without changing anything. And what that gives us is s plus 4 over s plus 4 to the 4 minus 2 over s plus 4 to the 4. And that, we can now cancel that with the power in the bottom. We'll have a cubed. Or restating it, we're looking for the inverse of s plus 2 over s plus 4 all to the power of 4. Well, that can be replaced by, through this decomposition, the inverse Laplace of 1 over s plus 4 only cubed minus 2 over s plus 4 to the 4. Now we have a much closer alignment with the form that we saw earlier, and we can certainly do a similar thing with the first term. We'll work through that on the next page. Having broken our expression into these 2 terms, we're interested in how we'd invert each term on its own. And so we remember what we found on the last page. If we were to take the transform of t cubed, e to the -4t, we would get this term here, which is the n and the t to the power n. We would get the n factorial divided by it would usually be s to the 4, but because of the shift here, we have s plus 4 to the power 4. And likewise, if we were asked the transform of t squared e to the negative 4t, we would end up with this number factorial, 2 factorial, over s plus 4 because of the exponential multiplier, and it would be cubed. And lo and behold, that's the form of what we have here. So we needed just a little bit of adjustment, specifically of the coefficients. This 3 factorial is 6. 2 factorial is just 2 times 1, so it is 2. So now if we look carefully, what we need to do is have the inverse of 2 over s plus 4 cubed. Is that what we have? Well, it's not what we have. What we had to do was multiply by 2 on top, and we're also going to have to divide by 2 out front. So we'll have a half of that. With the half and the 2 together, it's exactly what we were given in the problem. Likewise, to find the inverse of this term, we note that we can find the inverse of 6 over s plus 4 to the power 4. However, we don't have a 6. We would need to multiply that through by 3. Well, we can't just go ahead and do that. We have to counterbalance that with a 1/3. And lo and behold, we have constants, half and a third, and we have inverse transforms for whom the inverse is very clear because we computed it already in the forward direction. So we can copy down the answer, 1/2 the inverse of the s plus 4 over to the power 3 will be t squared e to the negative 4t, and we'll have negative 1/3 the inverse with the 4th power. That was this expression here. When we invert, we go back to the t values, and we have t cubed times e to the negative 4t.